Our next speaker today is Frank Schirrmeister from Cadence Design Systems. He's a Senior Group Director in Solutions and Ecosystem. His title today is Accelerating Verification and Implementation with Machine Learning for Electronic Design Automation. Frank leads the Solutions and Ecosystem aspects at Cadence Design Systems. He graduated from the Technical University in Berlin and moved to Silicon Valley in the late 90s. Intelligent systems as target applications and AI ML technologies are critical parts of his charter, and today he will describe how AI and ML increase productivity for chip and system development flows. Thank you.
Wonderful. Thanks for the introduction. Appreciate it. Glad to be here. So we'll talk for about 15 minutes, 20 minutes about AI, ML, and we'll do this EDA-wide, basically the different opportunities in the EDA design flow, top to bottom. But first, how are we doing this? The kind of applications we enable, I'm actually right now not from home, so we are all basically available from everywhere. There's ubiquitous hyperconnectivity with our phones, going through networks, going through data centers. So right now, I'm sitting here in a hotel room somewhere and presenting, and the data is transmitted through fast networks so that I can present this from anywhere in the world, basically. If you look at the amount of data that is transmitted from these sensors all the way to the cloud-guarded data center with different edge processing elements throughout all this, it's a very huge opportunity for electronics in general with all the data being transmitted. And it's an opportunity really, when you look at it across all the application domains, from consumer through hyperscale, mobile, comms, all the way to industrial, healthcare, and automotive. And simply speaking, the complexity of all this is so enormous that, as the previous presenters also pointed out, you really need to have the productivity enhanced of design flows. And productivity can happen at various stages throughout the design flow. You have to select IP at the very beginning. You have to verify your hardware, software to look for functional correctness. You have to implement chips in advanced nodes and package and integrate it. The whole 3D IC heterogeneous integration is a big topic. And then system analysis is a big topic as the different disciplines are getting closer and closer together, taking electronics, taking mechanical, electromagnetic elements all together. So EDA is a key component these days to enable chips and systems. It's an opportunity for EDA. What we'll talk about here today, given that all of you are in EDA typically or EDA users, we'll talk about how we are using AI ML to increase the productivity of EDA design flows top to bottom. I will not talk about the IP aspects. Those are really focused on the enablement, and there have been recent announcements throughout all EDA, including us, of new components in IP blocks that enable EDA. I will really focus on how do we get from ideas down to the transistors. And if you look at what the EDA industry has achieved over the last decades, it has been able to really keep the cost in check, and has done this by raising the levels of abstractions constantly. And every time we've done this, it was the same process. We were abstracting something, like we abstracted from gates to RTLs. We're modeling at a higher level, automate the implementation from a higher level description, capturing data, and basically have simulation analysis and optimization across those elements. And we did this at every step of the EDA productivity journey, if you will. And now when it comes to the high effort aspects of the design flow, we were really focusing the AI/ML activities are the high effort components of the development, which include the dark blue here, the physical implementation, verification and software stick out as very big components of the overall design cost. So that's where we are focusing as Cadence, and I think if you look across EDA, it's quite general. That's where we are focusing our efforts on by bringing in the data analysis, and we had a lot of data analysis or data created in the context of what Verifighter showed us this morning. You have these neural networks with inferencing, training, and reinforcement going also in the implementation, not only of the analysis and optimization, which is up here. And then there's this journey towards more and more autonomous operations of EDA tools, basically making the designer's life much more productive to really focus on the high-value design aspects and help with AI/ML to optimize the productivity here. So if you think about the complexity a little bit, this is a reference from Google here. If you just think about our day-to-day life and just get the idea here how complex the number of states are you need to optimize. Chess was pretty complex. Go was even more complex. And then this is a reference here from Google. If you go all the way down to things like chip placement at the end, it's like orders of magnitude, again, more complex. And you have to identify and look at parameters like the power, the performance, the cost, software. So then it's not only the chip needs to fit into its system environment. So the more the overall architecture considerations play a good role. So this is basically my ask for mercy if I try to explain to my family what we're trying to achieve in automating with EDA flows. So it's very, very complex, just to put some numbers out here, and Google did a good analysis here with this graph. So when you now look into ML and AI and electronic design and automation, the standard EDA design flow is to have this design data into your algorithm, have an algorithm create as an EDA tool the output of what I'm trying to do, like an optimized throughput for verification, faster coverage, and so forth. The first item where AI/ML plays is what we call AI/ML Insight. That's really where you are really capturing, if you will, some of the cost functions in neural networks that you have trained. Cost functions, and we'll talk about that in a couple of minutes. Cost functions like, for instance, the delay prediction and layout and so forth. So that's AI Insight. It's largely invisible to the user, the machine AI/ML Insight, which it just feels like a more productive tool that has been trained better. There's then also the ML Outside component, where it's really about capturing, if you will, the expertise, the know-how of the designers as the designers are changing options, preferences, constraints, and commands in the tools and operate it. So that's really the ML Outside operation, where you are really manipulating those parameters with reinforcement learning, with trained networks to optimize the overall usage of the tools and the output of the tools. So the opportunities in ADA are very, very significant across the flow. I mentioned IP on top. We have our Tensilica course, of course, as one of the IP components. Here it's all about the tools, using AI/ML from simulation and formal verification. I'll go a little bit deeper in these here in a minute. We have on the digital implementation side, we deal with delay prediction, optimizing the flow, but it goes all the way down to library characterization, through the custom IC, where we are optimizing SPICE simulation for more accurate response surface models. And in the PCB domain, you may have seen some of the activities we were involved in industry-wide, to deal with placement, routing, and it doesn't stop there. It goes all the way down to, or up, if you will, to system design and analysis with things like smart sweeps, predicting eye openings, and so forth. If you look at verification as part of the chip development efforts, it's a very big process. If you go from the idea on the left all the way to the post-silicon with the fabrication, and we all have our fingers crossed that everything's okay. RTL verification is a very high effort as part of the overall flow together with the software. The chart from IBS I used earlier was showing this as well. And it's both in sense of time throughout the project flow, which is left to right, as far and as part of effort, it's a very significant component. And functional verification has very significant areas where we can apply AIML to increase productivity and to increase throughput. So if you look at the regressions for functional verification, where you run until your regressions are finished, one of the things where in EDA this is applicable is the ability to really use machine learning to optimize at the end of the way the regression in the regression order in a way that you get to the same coverage but get to it at a faster time, improving really your throughput, your verification throughput here by getting to the comparable results faster, using essentially a way to run the verification, run the regressions in the right order, and reduce the simulation cycles while getting the same coverage that you would expect from a longer run. So this is really the results here in what we have seen in Excellium NL with up to 5 times efficiency, getting the same coverage. So you had much less CPU cycles to get to the same amount of coverage as you see here with the 99% in functional verification. And companies like Kioxia, you get the slides, achieved significant better turnaround while maintaining the same coverage of the original. That's one area. Another area is in verification is the formal verification portion, where you are optimizing resources and reproducing previous runs. If you look into the reinforcements learning applied here, you have this thing called proof orchestration in formal verification, where you have really the initial scan, and then you basically position your jobs throughout your available resources, running the different proofs. By applying reinforcement learning, you can dynamically adjust the engine selection, which of the solvers to use, and you get to a much steeper curve on the left-hand side here. These are 3 examples where you get to a much steeper curve to get to the number of determined properties. The way that's working is that you actually pre-train networks using examples. That's happening within the Cadence R&D team, where you're optimizing, training a network, and then figuring out essentially which are the best proofs, the best engines to use, and which engines to kick off the network if they're not providing the right properties and so forth. So that's on the formal verification side. Here's an example from ST Microelectronics. They got significant better proof out of the box and better regressions. Just for 30 seconds, I got the little note here that I'm approaching the last 2-3 minutes. Implementation to tape out the whole implementation flow. I know this is a more verification-centric audience here, but just to give you an impression, once the verification has been optimized, we are also working hard on better performance and productivity for the implementation flows, where it's here a typical example of ML inside and outside. You have the inside delay prediction, which is essentially a pre-route trained network that understands the delays. And then we have recently announced the Cerberus Intelligent Chip Explorer, which is ML outside. It's really automating the smart the design flows. And we have seen with customers like Renesas really great results here in automating the design flow optimization. So to drive it home, EDA is by far not done yet. It's an exciting industry. The hyperconnectivity I talked about at the beginning is essentially, if you will, job security for the next 20 years or so for us engineers. And we are approaching now this era of the golden age, as Professor Hennessy and Patterson called it, where you have very application-specific, domain-specific design and architectures. And there is much more to come with Aiml helping us to, across the flow, increase productivity. We talked about 2 examples here, and there's lots more to come. This is truly just the beginning of Aiml improvements throughout the flow. And we're working hard with our intelligent system design strategy to really bring together the system design, the IP, classic IP and chip EDA with the system design tools, and Aiml is all part of that. With that, bright future ahead. We have gone very far already. And yeah, I'm personally very, very excited being a small wheel somewhere here as part of the overall industry. We're making really, really cool, exciting stuff happen for hyperconnectivity and the whole technology-driven future here. That's it.
Good. Thank you very much, Frank. That was very interesting. We've got a few questions. The first one is XLEM ML regression able to find more potential bugs compared to straightforward plain random generation?
So it's all about how you apply the resources at the end. So that's a question which Michael Sullivan and I will take offline as well. But the objective here was to increase verification throughput and get to the same coverage faster. Of course, now it's a question how you apply. Now you have more, how you apply your resources. Now you have more time to do more bugs. So the answer is yes, it helps you to basically run more tasks and run more verification to find more bugs. In itself, it's really focused on the best coverage distribution there. But it helps you then to have enough time and enough resources if you choose to apply them this way to find more bugs.
Okay. One more question as well. So it seems that what you presented so far has been built into the tools by Cadence. Do you see any of your customers actually applying AI/ML themselves outside of the EDA, outside of your EDA flow?
Well, first of all, there's always this, when we discuss with customers about AI/ML, it's this mix of enabling their AI designs in their chips, making it as productive as possible, and do things there in our tools like having the ability to deal with highly replicative structures for verification and implementation, which is very important in AI-based designs. We are working closely with our customers, given that part of the AI/ML outside capabilities we are working on is, given that that's really capturing, if you will, the knowledge of the design teams as they're applying these tools. So we are working closely with our customers to get that knowledge into the design flows there as well. So it's a mix of both.
Okay, thank you. Okay, that was the last question. So just before you go, Frank, just a couple of thank yous. First of all, thank you very much for presenting from your holiday in Jamaica. Hopefully we'll let you go back to the beach
now. My pleasure.
And also thank you. It's always good to see a reference to Hennessy and Patterson in any presentation. Respect to those two gentlemen. So
I know those are amazing personalities helping to drive the history. Yeah, so they definitely deserve the recognition. Yeah.
Yeah, brilliant. Thank you very much. Thank you.